In the last segment, we talked about titration as a specific type of solution stoichiometry, meaning that you need a balanced equation and the mole ratio to move forward. In this segment, or section, we're going to talk about the last concentration unit, and this will be new to many of you, and that is molality. Molality gets the symbol little m, which is moles of solute per kilograms of solvent, and usually and typically the solvent of choice is water. All right, now this is typically used for something that we call a colligative property. And a colligative property is something that depends only on the fact that we have particles. We don't care if they're sugar particles or alcohol particles, sodium particles, chloride particles. We don't care. We're just counting particles. Now, usually and typically, this is vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. So what we're going to do is we're going to be typically looking at freezing point depression and boiling point elevation. So we have a new formula, delta T sub B KBMI, where delta T sub B is change in boiling point, which means you need to know what the original boiling point is. So for us, we're interested in water, and the boiling point of water is 100 degrees Celsius. K sub B is a constant that you go look up in a table somewhere. M is equal to molality, and I is equal to basically the number of particles. Okay, so this is where you need to know if you have something ionic and whether it's soluble. How many particles will it dissociate into? Or will it dissociate only partially? Or do you have something that's not ionic and therefore does not dissociate into particles, and therefore you only have one? Page 24. T sub F is change in freezing point. For water, freezing point is 0 degrees Celsius. If you have a different solvent, you would have a different freezing point, just like you would have a different boiling point if you had something other than water. K sub F is a constant. You would go and look that up somewhere. M is still molality. And I is equal to Van Hoff's constant, or the number of particles. Okay, so how do you know what the K's are? You look them up in a table. How do you know what the I's are? You have to know if it's ionic, soluble, or insoluble versus covalent or non-ionic. Non-ionic means you only have one particle. Okay, so let's give this a try. What is the boiling point and freezing point of 100 grams of glucose and 100 grams of water? KB and KF we're going to look up, and I've given them to you in the problem. Okay, so the first thing is delta T sub B equals KB times molality times I. K sub B is going to be 0.52 degrees Celsius per molal. The molality is going to be moles over kilograms. 100 grams of water is 0.100 kilograms, and therefore what we need is the moles of glucose. So I'm going to come over to the side and say we have 100 grams of glucose. We need the moles. Okay, molar mass, you would look that up and you would find that that is 180 grams of glucose per 1 mole. Add that up for the purposes of the video. We're going to speed that along. And we're going to find that we have 0.556 moles, and therefore our molality is 5.56 molal. Our I is the number of particles. This is not ionic, it's covalent, which means we only have one particle. Therefore, delta T sub B is going to be 0.52 degrees Celsius per molal times 5.56 molal times 1. Molal cancels, and we have degrees Celsius. So that's a good indication that you're doing the math the right way. We get out our calculator, we do the math, and we see that our delta T sub B is 2.9 degrees Celsius. Remember, our original boiling point is 100, and it's a boiling point elevation. So boiling point is going to be 100 plus 2.9, which will be 103 degrees Celsius, because this is not a body temperature. All right, we're going to do the same thing with freezing point. Delta T sub F equals K sub F times M times I. K sub F is a different value, 1.86, and I'm going to leave the units off this time for clarity, times 5.56 times 1. Delta T sub F is going to be 10.3 degrees Celsius. So remember, it's a freezing point depression. So instead of adding, a depression means we're going to subtract. So freezing point is going to be 0 minus 10. We're going to drop the 0.3, minus 10 degrees Celsius. Okay? Now, the same problem above, except that we have sodium chloride. Okay, so we want to keep the molality the same, and the point is, the only difference is that instead of our I equaling 1, sodium chloride is ionic and it's soluble, so I now equals 2. Delta T sub B is going to be 0.52 times 5.56 times 2. Delta T sub F is going to be 1.86 times 5.56 times 2. And what you end up seeing is that our boiling point elevation is double, or 106, and our freezing point depression is double, because we have more particles. Okay, so the point in this is that if you have more particles, your freezing point and your boiling point change is going to be more pronounced. So why do you think we salt the roads in the winter? To lower the freezing point. Why do you think water stops boiling when we add salt to it? Because we elevate the boiling point. All other things being equal, then, which substance would be the best de-icer? Okay, NaCl, I would be 2. PbNO3, 4, our I would be 5. CH3OH, the I would be 1. PbOH2 is insoluble, so it would be 1 point something. So clearly, this one, all other things being equal, would be the best de-icer because we get the most particles. In the next segment, we will move along with this concept and then wrap up our unit with solid state.